This is video 31 in the lectures on the design of reinforced concrete beams. This lecture explains the method of calculating the shear reinforcement. The optimum shear reinforcement coincides with the simultaneous failure of concrete and stirrups. This means that the Vrd max must be equal to Vrds. So the failure of the concrete strut will happen at the same time as the failure of the stirrup, of the tension rod. If you put in some numbers, then we can calculate cotangent theta, which is equal to what is written here, with x equals bs of x equals ASW FAWD divided by BS nu FCD. This is a kind of a mechanical reinforcement ratio against shear. Now suppose two approaches. First is a failure of the concrete strut, and second is a failure of the stirrup. In the failure of the concrete strut, we know this is the formula, this is the resistance, the shear resistance given by the struts. We can rearrange it in dimensionless units, and we have this equation. For the failure of the stirrups, we have this equation. We can rearrange it for dimensionless elements. And now we will take y1 equals to Vrd max divided by nu FCD Bz. X we already seen, and y2 we take it as this. Then in cotangent theta is the square root of 1 over x minus 1. Then we see that this equation here can be easily rewritten as a1 of x equals the square root of x times 1 minus x, which is a parabola. And the second equation can be easily written as x times cotangent theta, which is just a straight line. Now we will plot those two equations. On the x-axis we take x, which is in fact the shear reinforcement. On the y-axis we take the Vrd max. Then you can see that what shear reinforcement is concerned, you have all straight lines going to the point 0, 0, and it depends on the cotangent theta. If cotangent theta is 1, you got the green dotted line. If cotangent theta is 2, you have the blue dotted line. So every line between there is good. It's just depending on the angle of the compression strut. So for a given shear force, for instance 0.3, then the shear reinforcement is between 0.15 and let's say 0.3. It's clear from this that the bigger cotangent theta or the smaller the inclination angle, the least amount of reinforcement you need. But there is a limit. The limit is the red line, which is the maximum capacity of the compression strut. So you see easily that this point where the capacity of the reinforcement and the capacity of the strut is reached at the same time, there's this point, that's the optimum point, because you see that there's a first point which is okay, and you have the least amount of reinforcement. This is for cotangent theta 2. Now there is another point where the compression strut reaches its limit together with the reinforcement, which is on this side. So each cotangent theta, each angle of the compression strut has its optimum point of reinforcement. So we should stay on this red line when when calculating the shear reinforcement. So in fact, what we are doing is we are optimizing the angle theta. Now the shear calculation procedure. The design value of the resisting shear force is Vrd, and the design value of the imposed shear force is Ved. And we will just see how to calculate Vrd. We know that VRDC is the contribution of the concrete, VRDS is the contribution of the stirrups, and VRD max is the maximum capacity of the concrete strut. First, we check if the VED is smaller than VRDC. If this is the case, no shear reinforcement is needed because the concrete alone can take up the applied shear. Of course, there is always a minimum amount of stirrups needed. If VED is bigger than VRDC, then we know that we need shear reinforcement, and we need shear reinforcement until VED is smaller than VRD, and the main reinforcement, of course, must be able to handle the additional tensile force coming from the shear. VRD is, of course, the minimum of VRDS and VRD max. Let's now suppose a beam simply supported, loaded with uniform distributed load. The beam is cut off here in the middle because you are interested in what is happening at the support. This is the system line. This is again our beam, but then in the system line. This is the shear force diagram. And on a distance of d cotangent theta from the face of the support, we calculate VED. So the VED for the stirrups is calculated at a distance d cotangent theta from the support, from the clear face of the support. But at the edge of the support, there is VED at the support, just at the edge, must always fulfill the following equation. It must always be smaller than VED max. Why? Because force coming near the support will be diverted directly to the support, but this can only be done if the compression strut is working, if the compression strut is not failing. So it means that VED at the support must always be smaller than VED max, otherwise it will not work. So don't forget to check this. Your shear force to calculate stirrups is VED at a distance d cotangent theta, but you have to check the shear force at the face of the support. If you have a concentrated load near your support, then you can make this, then VED equals beta VE, and beta is smaller than 1. And the beta is a function of the distance of the concentrated load from the face of the support. Of course, that alpha AV, the distance, must be situated between d over 2 and 2d. The reinforcement, the shear reinforcement calculated this way must be put in the zone 0.75 times the distance AV, must be situated there in the middle. Of course, this same rule applies for instance, a corbel. Now we have VED which is the shear force at the distance of d cotangent theta, or in case of a concentrated load, it's beta times VE. We first check VED is smaller than VRDC, and VRDC, to summarize the formulas that we have seen, is given by this formula. If VED is bigger than VRDC, then in this case we check VRD max. We check if the compression strut is not failing. So for that we calculate VRD max, and VED must be smaller than VRDS, so we calculate the needed stirrup reinforcement. So this is the shear calculation procedure. The ASW over S, the needed shear reinforcement, is given by the cross-section of the rebar multiplied by the number of legs of that the stirrup has, divided by the clear distance of the different stirrups. And just to give you an idea, if you have a diameter 10 with 2 legs, a diameter 10 every 200 millimeters, it's roughly 0.8 as the stirrup reinforcement ASW over S. For a diameter 8 with 2 legs every 200 millimeters, or 5 per meter, ASW over S is 0.5. So this table gives you a rough estimate of how those figures, how it works. And then finally, the number of legs in a stirrup. If you have here just a normal stirrup, then of course there are 2 legs. It can also be 2 separate legs in one cross section. It can be a non-closed cross section, and this is, for instance, the case a combination, which is 1, 2, 3. It's 3 legs in one stirrup. This is the front view of the beam. S is the distance center to center, the distance center to center of the stirrups. You can also have inclined bars. Then alpha is 90 degrees instead of alpha is then 45 degrees instead of 90. Then the distance center to center is then S, and it can be inclined bars like that. Can also be used as stirrups. You have one front face and one at the back face. So you have one this and one there. So this is also N is 2, but alpha is 45 degrees. The geometric shear force density is defined as ASW over S divided by BW times sinus alpha. BW is just the width, the minimum width of the section. The minimum shear force density, this is the minimum stirrups that you have to provide, is 0.08 square root FCK divided by the yield stress of the stirrups. The maximum longitudinal spacing of the stirrups is 0.75 D if cotangent theta is 0, when you have stirrups in 90 degrees, is 0.75 D. The maximum longitudinal spacing of inclined bars is 0.6 D. And the maximum traverse spacing, which means the spacing between the legs, is 0.75 D and must always be smaller than 600 millimeters. So these are the geometrical rules. You can now calculate the needed shear reinforcement in a section, and see you next lecture.